All right, in this lecture, we're going to work through a full factorial ANOVA example. I think that it's really good to see it all put together in terms of the design, the hypotheses, and importantly, how we are able to obtain our various F statistics so that we can draw conclusions about our hypotheses. So this is a kind of applied example, specifically from stuff in my research. And this is fictitious data, but the overall research question is something that my lab is interested in studying. So in my research, I want to see whether sexual orientation, heterosexual or LGB, so this is our first factor, so factor one. And factor one has two levels. You're either heterosexual or belong to either lesbian, gay, or bisexual. And relationship status. So relationship status is my second factor. And because we have two different factors, we should immediately start thinking about a factorial ANOVA design. So in a relationship or single. So this factor has two levels. You can be in a relationship or you can be single. And I want to see whether these two factors interact to affect perceived stress levels. So perceived stress levels here is what I'm measuring. So this is my dependent variable. I obtained data from 20 subjects. So 20 subjects, and I record levels of perceived stress. The stress ranges from 0 to 40 with higher values indicating more stress. So this is an interval/ratio data piece, right? The 0 represents an absence of stress, 40 is the highest level. So we have four total groups in our design: heterosexual single, heterosexual in a relationship, LGB single, LGB in a relationship. So again, factor one, we have heterosexual or LGB. So these are our two levels. Our factor two, we have relationship or single. And so we look at this, there are four total groups. So in this factorial ANOVA design, this is a 2x2 ANOVA because we have two independent variables. Each of the factors have two levels. So there are 2 times 2, 4 total groups. We have 4 cells. So what we're asked to do is to compute a two-way ANOVA using a 0.05 level of significance. So that's our alpha value, what we're going to be using to find our critical F values, to determine whether or not sexual orientation and or relationship status affect perceived stress levels. So remember that in a factorial ANOVA design, we have 3 hypotheses. So we have 3. We have the main effect of factor A or factor 1. So main effect 1. So this is for sexual orientation. Our null hypothesis is that these two levels are equal to each other. And again, because we're using inferential statistics, we need to write this in relation to our parameter. So mu1 is equal to mu2. Stress between heterosexual and LGB participants are the same. There's no difference in stress levels between heterosexual and LGB participants. Then we have our alternative hypothesis. We say that stress levels are not the same. We say that these means are not equal to one another. Typically, in a factorial ANOVA, we're just going to use the notation not equals to, right? Even if we just have two levels. So this is a main effect of sexual orientation. This first hypothesis is testing for this main effect. So collapsing across relationship status, is there a difference between the levels of this first factor? The next hypothesis we write about is the main effect for factor two. So this being the main effect for relationship status. So our null hypothesis is that mu1 is equal to mu2, meaning that these two groups are equal to one another. We can say that stress between those in relationships and those that are single are the same, or that there is no difference in stress levels between those in relationships and those who are single. The alternative hypothesis here is that they are not equal. Stress between those in relationships and those that are single are not the same. There is some difference going on. And again, we'll use the not equals to sign here when we're writing our alternative hypothesis. The last hypothesis is for the interaction between the two factors. So this is for the interaction effect. So our null hypothesis is that there is no interaction between sexual orientation and relationship status on stress levels. The alternative is that there is an interaction between sexual orientation and relationship status. There's not really a great way symbolically to state whether there is or is not an interaction. We just write it out here that there is either none or that there is an interaction. So these are our three hypotheses. And because we have three hypotheses, we are going to obtain three F values to allow us to test whether we can reject or retain each of these hypotheses. So here's the ultimate design. Here's some made-up data. But here we have factor one, orientation. Again, two levels. That's where the two comes from. Then we have factor two, which is relationship status with its two levels. That's where the other two comes from. So a 2x2 ANOVA. And we measure levels of stress. So again, in each of these particular cells, we have an N of 5 in each of these cells. And we have a total sample size of 20. Now, when we talk about collapsing across variables, we mean how many people are heterosexual and how many people are LGBT. Well, it doesn't matter if you're single or in a relationship. If you're a heterosexual in either of these, you're still heterosexual. So there is 5, 10. So there is 10 heterosexual individuals. How many people are LGBT? That's 5 plus 5 is 10 LGBT. So we're concerned with 10 versus 10 in this collapsing. Same thing with relationship status. How many people are single? Well, it doesn't matter if you're heterosexual or LGBT. If you are single, that's all that matters here. So there are 10 people who are single, and there are 10 people in a relationship. Notice that if you add the rows, you get 10 each. So that gives you the total sample size. If you add the columns, the total number there, you get 10 each. That gives you 20. Now, the setup in Jamovi is going to be important, and this is an extension of our between subjects design where we utilize nominal variables. So because we have two factors, we now need two variables with their specific levels written out. So the first one, we have sexual orientation here. And what I've done is I've just placed 10 individuals being heterosexual, 10 being LGBT. That's perfect. That's perfectly fine. Now, when you write the second factor and you are stating the levels of that other factor, you can't just put single 10 and in a relationship 10. Because remember that we read across the rows to identify which groups people belong into. So for instance, these first 5 people are in the cell for heterosexual single. And these are their scores. And you can see that if we go right back here, 20, 25, 22, 15, and 20. The next 5, we have heterosexual individuals in a relationship. So again, reading across the rows, we have 10, 12, 15, 10, and 11. And that matches again here, 10, 12, 15, 10, and 11. Then the next 10, we have LGBT single. And there's 5 of them. 30, 35, 40, 28, 40, and 37. 30, 35, 28, 40, and 37. And then the last 5 individuals make up the last cell. So we have LGBT in a relationship. So 20, 22, 30, 22, and 19. And those are, these scores here, 20, 22, 30, 22, and 19. So these are where our 20 values are coming from and how we organize that in Jamovi. If we're only measuring one dependent variable, then you're just going to need that one column for your dependent variable. So let's talk about what we can do ahead of time to save ourselves some effort and stress later on. So these are some preliminary calculations that I highly recommend that you do. So here, I highly recommend that you find the sum of the x values and the sum of the x squared values within each cell or group at the very beginning. Before you're doing a lot of the stuff with the sums of squares formulas, what I recommend you do is in each of these cells, go ahead and solve for the sum of x's and the sum of x squareds. So the sum of x's is just the sum of the scores in that cell. The sum of x squareds is taking each of these scores and squaring them within the cell and adding them all up. This will save you a lot of time later on in your calculations because you're going to have to be using a lot of these sums as you're doing your sums of squares between groups and your sums of squares total, okay? So feel free to pause the video, make sure that you can input these values and you're getting the same numbers. So next step on the preliminary calculations before we start jumping into our sums of squares total and our sums of squares between groups, etc., is that you should find the sum of x values in each level of factors a and b, collapsing across the other factor. So what this means is we should find the sum of x's for single. Now, again, it doesn't matter whether you're heterosexual single or LGB single, you're still single, right? So adding the sum of x's in this cell and this cell will give you that 272. Adding the cells in a relationship and LGB, or for heterosexual and LGB, gives you 171. And I've gone ahead and written here and highlighted where these numbers are coming from. So this is collapsed across orientation. Then here we have collapsed across relationship status. So again, it doesn't matter if you are heterosexual single or heterosexual in a relationship, you're still heterosexual. So adding your sum in each of these cells will give you that 160. Adding the sum in LGB single and LGB in a relationship will give you the sum of all LGB participants, okay? And so now that we have these preliminary calculations, and what I've done is I've kept these calculations present in this slide so that you can see where we're pulling these numbers from. So the first thing we should do is solve for our sums of squares total. That's usually always recommended just because remember that we are partitioning our sums of squares total into our sums of squares for our first factor, sums of squares for our second factor, sums of squares for our interactions, and then sums of squares for our error, right? And so when we do that, if we already know what it has to be, ultimately what these components have to add up to, then we also know what these particular values are confined by. So our sums of squares total is the formula that we've used so far this entire semester. Sum of x squared minus the sum of x squared over n. And when we're talking about this formula, we're going to be concerned with every value. So how do we go ahead and get sum of x squared? Do you want to square 20 values altogether? No. But if you'll notice, we've already done a bulk of the legwork here, right? So 2629 plus 5878 plus 2134 plus 690 gives us 11,331. Then, if we take the sum of x's, we can just sum these four values, 102 plus 58 plus 170 plus 113, which gives us 443. You could also add these two sums together, and that would give you the right answer. You could also add these two sums, and it would give you that right answer. 443 squared over 20. So we have 11,331 minus 196,249 over 20. Remember that order of operations, we need to do this term as a whole first. So we square, then divide. So we get 11,331 minus 9,812.45, which equals 1518.55. Now we know this is going to be broken down into four components. Going to be broken down into four components. So we know that each of these sums of squares can't be greater than 1518.55. And we know that these four will all add up together to give us 1518.55. So that's our sums of squares total. Again, pause the video after each of these steps of the calculations to ensure that you can also get these values and you feel comfortable with getting them. Because when it comes time for an exam, you'll be able to use these steps in solving for your factorial ANOVA. Now we're going to start looking at our sums of squares for our specific main effects. So this is the sums of squares for orientation, okay? So we are interested in the orientation variable, the orientation factor here. So this should look familiar to you because we've used this in the one-way between subjects ANOVA. We've used this with the one-way within subjects ANOVA. Now we're using it here. But the thing to keep in mind is that we are going to be working with collapsed values. So how many groups are in this particular factor, orientation? How many levels? There are two, right? And so when we are summing, sum of x sub k squared over n sub k, k is equal to 2 for this particular main effect or this factor. So we're going to have two divisions, two things that we're going to be adding up. So the first is heterosexual. Well, the sum of x's in that first group is 160. 160 squared over, we have 10 total people who are heterosexual, plus, and we're summing because we have the sigma notation outside the bracket. We add LGB, we get 283. 283 squared over 10. In the brackets, we're going to sum these up. And we subtract from that the 443 squared over 20, which is what we used in the sums of squares total. Now, remember, you can never have a negative sum of squares, okay? So please keep that in mind. So here, we have 2560 plus 8008.9 minus 196,249 over 20, which gives us 756.45. That's our sums of squares for our first factor for orientation. Now we look at the main effect for relationship, the sums of squares for this second factor. And again, what is our k value here? How many groups do we have for a relationship? We have two. So we're collapsing across the level of the second factor when we are doing this calculation. So the sum, sigma, of sum of x sub k squared over n sub k. So the sum of x's for those who are single, right? We have 272. 272 squared over 10 because we have 10 total single individuals, plus, and we add because we have the sigma notation here, 171, which is the total sum across this row, divided by 10, minus, and again, we use the same value here, 443 squared over 20. So here we get 7398.4 plus 2924.1 minus 196,249 over 20 gives us 510.05. And it's always good to write these down so that you are able to reference these. So we know that the total is 1518, 756 is less than 1518, so is 510, and 756.45 plus 510 is still less than that 1518. So we're so far, so good. Now we're going to do the sums of squares for the interaction. And this is where we're going to see this kind of funky formula here, but it's not too funky because it is really the same as what we've looked at so far. Sigma outside the bracket just means that we're going to sum up everything inside the bracket. But now we're writing sigma x sub cell squared over n sub cell. So what does that mean? Well, how many cells do we have in our factorial ANOVA? Well, in a 2x2 ANOVA, we're going to have 4 total cells. We have single heterosexual, single LGB, interrelationship heterosexual, interrelationship LGB. So there are going to be 4 things that we're going to be adding together. Heterosexual and single, heterosexual interrelationship, LGB single, LGB interrelationship. This is where having those sum of x's in each of our cells helps us streamline this process because we're going to have to sum the x's and square them. So 102 squared divided by how many people are in each cell? 5. So 102 squared divided by 5 plus 58 squared divided by 5 plus 170 squared divided by 5 plus 113 squared divided by 5. Put this back into the brackets because, again, that's what's found in this bracket, minus 443 squared divided by 20. In the interaction sums of squares, you must also subtract the sum of squares that you have found for factor A and the sums of squares you have found for factor B. You must subtract these values when you are solving for the sums of squares for the interaction. If you do not, you will get an incorrect answer. So we take our sum here and we subtract 443 squared over 20 minus 756.45, which we solved for orientation, and 510.05, which we had solved for relationship, our second factor, and we get a value of 8.45. Now, what's nice about the sums of squares for error is just that we take our total and we subtract our three components that we've solved for. Because we know the sums of squares total is partitioned into 4 parts, if you know 3 of the parts, then you know the 4th. So 518.55 minus 756.45 minus 510.05 minus 8.45 gives us a sums of squares error of 243.6. Now for our degrees of freedom. What's nice in a 2x2 ANOVA is that all of your main effects and your interactions are going to have a degree of freedom of 1. And then you'll have to calculate the error. So the reason why we say that is because the degrees of freedom for factor A is just Ka minus 1. The number of levels in that first factor minus 1. So 2 minus 1 is 1. Degree of freedom for factor B, relationships. How many groups do we have? Kb. That is 2. 2 minus 1 is 1. To get the degrees of freedom for the interaction, we multiply the degrees of freedom of A times the degrees of freedom of B. So 1 times 1 gives us 1. So these are going to be the numerator values. So remember that when you're looking at your critical F table, you have 2 degrees of freedom values that you will be consulting, a numerator and a denominator. And remember that the denominator degrees of freedom value is that for error. So how we solve for the degrees of freedom of error is taking Ka, which is just the number of levels in factor A, so 2, times the number of levels in factor B, 2, multiplied by lowercase n minus 1. Lowercase n is just the number of individuals, animals, etc. in each cell. So how many people do we have in each cell? Well, there's 5, 5, 5, and 5. So that is 5 minus 1. So 2 times 2 times 4 gives us 4 times 4, which is 16. So we know that the degrees of freedom total is partitioned. So degrees of freedom total partitioned into degrees of freedom of A, B, the interaction, and error. So if we add those partitions up, we get our degrees of freedom total. So we can also do this by n minus 1, capital N minus 1. So we know that there are 20 total people. 20 minus 1 is 19. If we add 1 plus 1 plus 1 plus 16, that gives us 19. So a really nice way to be able to just check ourselves and make sure that we are doing things correctly, right? All right. Now we find the critical F values. So in our F table, we consult the specific F table for alpha of 0.05. That is important. That's what is given to us in the question, alpha of 0.05. Now, for our F value for our factor A and factor B and interaction, in a 2x2 ANOVA, they'll all be the same because remember, the degrees of freedom for each of them is 1 for the between groups. The error is the same, 16. So here we have 4.494. So this is going to be the critical value that we are going to use when we are evaluating whether our obtained values for each of these factors and interactions is significant, 4.494. So we can go ahead and write out the ANOVA summary table. We have our source. And I've gone ahead and just written out the factor names here. So orientation, relationships, A times B, orientation times relationships. So this being the interaction. Error and total. We have our sums of squares, which we've calculated. These all add up to 1518.55. Our degrees of freedom. Sums of squares divided by degrees of freedom gives you variance, or as it's oftentimes written, mean square. So 756.45 divided by 1, 510.05 divided by 1, 8.45 divided by 1, 243.6 divided by 16. That gives us our error variance. And then we calculate our three F values. So for orientation, we take 756.45 divided by 15.225, which gives us 49.68. 510.05 divided by 15.225, and then 8.45 divided by 15.225. Remember, in a basic ANOVA, the F ratio is that variability or variance between groups over the variance within groups or error. So when we go ahead and add our factors into our ANOVA portion for Jamovi, and you're going to select just the regular ANOVA option, similar to how we did that with the between subjects one-way ANOVA, and we move our dependent variable into our dependent variable box, we get our nice summary table with sum of squares, degrees of freedom, mean square or variance, our F statistic, and our p-value. So we have significant main effects for sexual orientation and a significant main effect for relationship, but notice that our p-value for the interaction is greater than alpha, greater than 0.05. So we say that we fail to reject the null hypothesis for the interaction, but we can reject the null hypothesis for our main effects. So here are our conclusions. So for sexual orientation, this was for factor A. We reject our null hypothesis. We have sufficient evidence to show that stress levels are significantly affected by sexual orientation, p less than 0.05. For relationship or factor B, we can say that we reject our null hypothesis. We have sufficient evidence to show that stress levels are significantly affected by relationship status, p less than 0.05. Then we have an interaction. So when we have our factorial ANOVA, we must have three conclusion statements. Now, in the interaction, our p-value was greater than 0.05, which means that we fail to reject the null. We say that there's insufficient evidence to conclude that sexual orientation and relationship status interact on stress levels, or stress levels are affected in a way both by sexual orientation as well as relationships and how they interact with one another. Now, what's really important to be able to do in a factorial design especially is to produce a plot. And so plots allow us to visually inspect interactions like we saw in the first video on factorial ANOVAs. So when we look at plots, we're going to go down to estimated marginal means. This is going to be the drop-down menu that will allow you to produce a plot. You're going to move your two factors into the same term, and you can do Control A, or you can type both of them or move both of them with a little arrow into the same term. Moving them into the same term will produce both of these factors in the same specific plot. So by default, you'll have marginal means plot listed here. And so sexual orientation here on the x-axis, you have your dependent variable on the y-axis, and then the colors of the line represent your second factor. So notice here that we have a main effect of orientation, right? So if you averaged these two together here, you'd probably get something around here. If you averaged LGB and LGB in a relationship and LGB single, you'd probably get a value kind of right here. So again, there's a pretty big difference between the stress levels of LGB and heterosexuals, right? That's the main effect. In relationships, right? So single, if you were to average the single, it'd probably be something like here. If you were to average the in a relationship, it'd be something about here. And we have a nice kind of difference, a mean difference here. But do the actual plotted lines intersect? And the answer is no, they do not intersect. So we can look at this a little bit more clearly here. Each of these lines are running roughly parallel, right? So in a relationship, it doesn't matter whether you're heterosexual or LGB. If you're in a relationship, the values of stress are typically lower, right? Same thing with single. If you're single, it doesn't matter whether you're heterosexual or LGBT, the values are higher, right? And so in interaction, just as a general point of review, interactions are typically when you have intersecting lines where levels of one variable are influencing levels of another. If you have parallel lines, that's usually a good indication that there is no interaction. But whether it's a significant interaction or not a significant interaction, you would definitely want to confirm that with your calculated statistics. Now, going back here, just as a point of reference, you can click and hold one of these factors and move it up. And by doing that, you'll actually change which specific variables are found on the X and which are found in different colors. So the last thing we can also do is look at effect size calculations. And so this is typically important, especially when we have significant p-values. So again, we're kind of going a little bit beyond the p-value. And the way that we solve for this is we take our sums of squares for that specific factor and divide that by our total minus the sums of squares for the second factor minus the interaction. And that will give us a decimal value, which when we multiply by 100 will give us a percent. And we can interpret that in the same way that we've interpreted it so far when we've been doing ANOVAs. A certain percentage of variability in our dependent variable can be accounted for or explained by our independent variable. So we get 0.756 for our eta squared for orientation, which says that 75.6% of variability in our stress scores can be accounted for by orientation. If we're doing eta squared for our second factor, we get 0.677. This says about 67.7% of variability in stress scores, our dependent variable, can be accounted for by relationship status. Then we look at our interaction effect, and remember our interaction effect, we failed to reject our null. We had a p-value of greater than 0.05. And so it makes sense that this value is relatively small. We see only about 3.4% of variability in stress scores can be accounted for by the interaction between orientation and relationship. And we can confirm these values here. Specifically, when we're working in Jamovi, we want to ask Jamovi to give us the partial eta squared. The partial eta squared is going to give us, again, that effect size. And it's going to be the correct effect size. There is a subtle difference with how eta squared and partial eta squared are calculated in computer programs. So here we have our partial eta squared, which matches the values that we've calculated using the formula that we just saw.